All right, so I'm going to do, I think, two more examples here. This is example 3, and then we'll put up one more after this, example 4, and you've got a homework assignment now. So hopefully this should be enough to get you guys on sort of on the right track here. So this particular example, I'm going to give you a stress state, and it looks like this. So we're going to have, and again, I'm going to draw everything in the positive direction, right? And then if it's negative, I'm just going to use a negative sign when I sort of, quantify the magnitude. So in the sigma xx direction, we have a minus 1 ksi. We have a 3 ksi of shear, that's positive. And then we've got a minus 5 ksi of axial force in the sigma yy direction. Right? And what I'm asking you is, first of all, will the concrete crack? And I'm telling you that this particular piece of concrete has a tension capacity of 0.5 ksi, so about 500 psi. And so the process that we want to go through here would be to plot the Mohr circle, identify what the maximum principal stress is, sigma 1, and then if that is greater than 0.5 ksi, then we're going to predict cracking. Right? And I want to show you one other thing that we can do with this is if it's greater than 0.5 ksi, one of the things that we will know is that since concrete cracks due to principal tension, we also generally know the direction of that crack, and that would be perpendicular to the principal tension stress. Right? Okay, so let me go ahead and let's draw the Mohr circle for this guy. So I'm going to do it way over here because we can see everything is pretty much on the compression side here. So this is my sigma and this is my tau. All right. And we're going to start by plotting those two, right? And I'm going to do it in blue since that's where since the cube there is in blue. So minus 1 and then minus 3 will put us right here, right? Sorry, positive 3, minus 1 and positive 3 will put us here. So this is minus 1 comma positive 3. And then we're going to go ahead and plot this side, right? But we're going to plot the sigma yy, then we're going to plot the minus tau xy, right? Again, because of the coordinate system. We're actually plotting the stresses on the x prime face, technically not just the y face there. Okay, so 2, 2, 3, 4, 5, and 3. It should be right about there. So this guy is minus 5, minus 3, like that. All right. And then I can draw a straight line between them. And that blue line there corresponds to the orientation in the upper left. Right. So this is the x and this is the y. Oh, that was a pretty messy y, and that's the y, right? Okay, so now let me draw the circle, right? So I'm just going to spin this guy right around, and hopefully I can do that. This isn't really working. Hold on. So let's see. This is 3.6 would be there. This guy, and then 3.6 and 3.6, something like this. Let me see if I can do a little bit better than that. All right, perfect. So that is our Mohr circle, right? So that is associated with, so every pair of shear stress and normal stress that this particular stress cube can experience, depending on how I rotate it, right, is represented right here. One thing I should point out, I guess I'll do it in black because it applies to everything, is that the center of this circle is actually at -3, 0. Right, so that's the center of the circle. We can solve for the radius of the circle, right? So let me do this in blue, I guess. I'm going to draw this line here and this line here. I'm going to just make them sort of double thick. They're really the entire length there. And this guy would be 3, right? And this guy here would be 2, right? So my radius here is just going to be the square root of 3 squared plus 2 squared. And when you work that out, you get that the radius is 3.6. And again, that's going to be in KSI because every sort of spatial dimension on this plot is in KSI, right? I can sort of accentuate that here, right? And it could just as easily be in KPA, right? It's all units will work, right? So then I will get that sigma 1, which is right over here, right? That is going to equal -3 plus 3.6, right? So this is sigma average, and this is plus the radius, right? So sigma 1 actually equals 0.6 KSI, okay? And you can also come over here if we cared, I don't know if you do or not, but you could write that sigma 2 actually equals -3 minus 3.6, and that would be a -6.6 KSI, just like that, right? So those are my extremes, right? The 6.6 KSI in compression doesn't really bother me too much. Concrete's really strong in compression, but the 0.6 KSI in tension, that is troubling when I know that my concrete can crack, when the tension exceeds 0.5 KSI, right? So the one thing I know, and I'm going to just write yes here, right? If the principal tension is greater than that, which it is, then I'm going to predict that this thing is going to crack, right? So the next thing we can do once we know that, or once we believe that this is going to crack, I can calculate the angle of principal tension, right? And that angle of principal tension will be 2 theta p. In fact, let me do that. Sorry, I'm trying to do everything on one slide here, and I'm starting to run out of real estate. I want to save this lower left. So let me try this. 2 theta p equals the inverse tangent. In this case, it will be 3 divided by 2, right? Because it's opposite over adjacent. The opposite, right? This sort of line here is 3, and the adjacent is 2, just like that, right? You can actually see it on the other side, right? This is also theta p, right? Okay, so you plug in, and you actually get that theta p equals 28.2 degrees, and it's in the counterclockwise direction, right? And you can see that just from the diagram. Basically what I'm doing is I'm taking these points here and I'm rotating it counterclockwise. So this point moves to sigma 1, right? That's sort of what's happening here. Okay, so we're rotating it counterclockwise. So what I can do here then, and I'm going to draw it in red, is I know that this particular face here, right, that guy has got to rotate 28.2 degrees, right? And then that face is going to have a positive 0.6 KSI on it, right? So let me draw that now in the lower left, right? So it's going to look something like this. Right? Where this particular angle is 28.2 degrees, right? And then the stresses, right, this guy, my stresses look like this, right, because it's principal stress. These guys are minus 6.6 KSI. And this guy over here is positive 0.6 KSI. So if I want to know and predict the angle in which this would crack, right, I would predict that it's going to crack just like that, right? Now I'm showing it as a rough crack. Concrete obviously is a composite material. There's aggregate and sand and cement and all sorts of things in there. But what we would know is that in general, the orientation of that crack should be this same 28.2 degrees, right? Because that is the angle that would give us perpendicular to the direction of principal tension, right? So if you go out to, if this was a structure and you're calculating this, right, you would expect if you go out to the field and you see that it has in fact experienced this state of stress, you would expect to see cracks at roughly 28.2 degrees, right? They won't be exact. Again, you know, the strength of concrete does vary. There's a lot of variability in it. But on average, you should expect to see cracks somewhere in that, 25 to 30 degree range. And that would verify this analysis. All right, so that's it for example 3.